Thank you very much, Gennady. So I want to thank Devika and Gennady and Ihor for this initiative. I think it's great, and I'm really excited that so many people are interested in this field, and I think there's an enormous opportunity here. And the other thing is, of course, to rectify. I had a promoter, and for example, Max Viergever and many before me, so I'm definitely not the godfather of medical image analysis in the Netherlands. I think the real pioneers started way before me. But we were lucky, I think, in our field that we are part of the AI revolution. When I entered the hospital as a physicist, you really had to explain what you were doing, and then they asked you to fix your computer problems. And I think that has changed. So I think the importance of the field in biomedical research and health has changed quite a bit. And you can see it, I think, because of this very wide audience here that all are interested in these technologies. So this is just a disclosure. So what I would like to do today is demystify a little bit about AI, because I assume there are, on the one hand, I see people that are very advanced and are utilizing or developing AI or using it. On the other hand, I think there's also people that are just interested to see what it could do for them. So in my lecture today, I would really try to cover some basic notions in order to really explain what AI is, what the current fuss is about, and what it is and what it is not. So if you think of AI as a definition, AI is the broad term. Then we have machine learning, and then we have deep learning. And to explain it, if you look at artificial intelligence, a lot of people, that if people talk about AI now say, oh, this is not really AI that you're doing, it's just machine learning. I think that's not the correct phrase. AI, I think, is the umbrella. Anything in which you make a computer do something which you can associate some intelligence, human behavior, you would call artificial intelligence. Now, within artificial intelligence, the field that has seen so much interest, both from academia and from companies, is the field of machine learning. Machine learning is a sub-part of AI technologies, and it's that part in which you teach a machine to do something. And typically, we teach a machine to do something by providing it with examples, and we let it learn from the examples in order to develop some kind of internal algorithm in order to start to mimic a certain task. And this is really the field in which we see most happening in medicine. And the overall idea is if somewhere in medicine, someone is performing a certain task, and especially if you're at an advanced state and you've really tried to optimize this task and you've standardized the task, then actually you collect a lot of data in the meantime. And if you give that data to a machine, why not let the machine learn to maybe partially automate the task? For example, in order to provide the task in places where there's not sufficient clinicians, or in order to reduce errors. Now, that's machine learning, and then the subset of machine learning is deep learning. And deep learning is simply that you are learning a neural network that is very deep. The name neural network clearly comes from the link with the human brain, in which you have different layers of neurons that are connected. Deep neural networks can now be hundreds of layers deep, and basically they are connecting input and output through some kind of network. And the process of machine learning or deep learning is try to build such a network to perform a certain task. So these are not new technologies. Deep learning exists since 1958, the concept, perceptron, etc. The reason you've not heard from it until recently, because it was for a very long time just a very poor technology that performed very poorly and took a lot of time. When I did my PhD in the 90s, I knew one or two groups, one in the Netherlands and one internationally, and we were always joking of the people that were building neural networks, because they were providing this beautiful reason why their approach would work, and then the moment they would apply it, they would calculate for hours, for days, and then end up with a model that was inferior to all the model-based and knowledge-based approaches we had nowadays. Luckily, for many years, people have been evolving the field, and now it has come to the state where it's actually often outperforming knowledge or model-based approaches. So what is the idea of machine learning? So normally if you're, I'm a physicist from background, so actually initially my intuition was that deep learning was never going to work so well. I thought we put so much thought into building these models and we describe our environment. How can such brute force methods as deep learning really work? So the way I like to work always, you have some input data, you model the world, the heart or the brain or a disease, and then given input data and the model, you generate an output. And that's the way a normal model-based approach would work. So it's different with machine learning. So in machine learning, you actually provide both the input and output to the machine learning algorithm, and the machine learning algorithm then builds a model which best maps the input to the output given the examples. Then you create an optimal model, and this process has really been improved over years and years. It's very, you have to be very careful not to overtrain, not to introduce biases, etc. But this is the field in which the methodology has developed quite a bit. So you build an optimal model given examples, and then if you have new input, you apply the model in order to generate output. So in principle, you don't have to really start to describe or understand the environment. There's approaches that really make an algorithm learn by itself what should be the optimal algorithm. Now, how should you view this? If you look at my field, the field of medical image analysis, in a way, what we really would like to achieve is to use optimally the rich information in image data in order to provide a diagnosis or a prognosis in order to do some clinical decision support. So there's different forms of machine learning, and I show this example to show the difference between what we call conventional machine learning and deep learning. So in conventional machine learning, what we do is that we first use some handcrafted features. So we think of a certain problem and we think this is important information. For example, if you're interested in the brain, you can look at the volume of the brain, the volume of the white matter, the volume of the gray matter, the presence of white matter lesions, and you have a computer compute these quantitative markers, and then once you have these quantitative markers, you see what combination of these quantitative markers relates to a certain relevant clinical endpoint, a diagnosis, a risk profile, or a prognosis. So this is, you can even do this with statistics. The moment when it becomes a little bit more towards machine learning is that if you don't compute one feature, but 10 features of 100 features. In the field of radiology, one field which has become very popular is the field of radiomics. And in radiomics, the underlying idea is that there is much more to an image of a tumor than just certain imaging markers you can think of. Perhaps if you would describe as a radiologist an image, you would think of the volume of the tumor or the regularity of the boundary. But in practice, you see a whole pattern, and there is a certain way this tumor is vascularized, oxygenized, and there's a lot of ways to produce images with different contrasts. So it's quite likely that a lot of things are going on and are visible that are very difficult to contain in just a few quantitative descriptors. And then the field of radiomics comes in because this is just brute force computing hundreds of features. So you go locally in an image and you compute the intensity, and then you blur the image, and then you look at the gradient, and then you look at the gradient of the gradient, and you look at the texture, and you make a whole library of, it's totally redundant. It's a little bit ridiculous almost that you would compute so many features of an image, but then once you've computed all these features, you assume that some of these features correlate to some of the underlying biology that is maybe linked to a relevant clinical output, and then you have some machine learning algorithms to compute which combination of features best link to the relevant outcome. And that is what you train in the training stage, and this way you build models. So it's actually quite, it's really statistical methods. The only thing is the statistics is a little bit more complex. Now, what is then the difference between machine learning and deep learning, conventional machine learning and deep learning? So in conventional machine learning, here is an example for classifying a car. So if you want to know whether a car is present in the image or not, do you realize that you're actually providing Google with training data whenever you have to check whether you are, what you're seeing in the image, all those labels you do, you're actually providing input for algorithm building for free. But so you can compute features, a number of features from the image, and then classify the image. But you can do also something else, and that is what a deep learning algorithm does. In a deep learning algorithm, all the pixels, all the voxels of an image directly input to the first layer of your neural network. Then you have a number of layers with all weights, and at the end you have an outcome. And the outcome could be binary. If you would train a network to just say there's a car or there's not a car, you only need one output, a 0 or a 1. A 1 means there's a car. Then you have this long layers of neurons. You provide the input data directly to the network. You have the number of weights. And then there's an optimization stage in which you try to constantly update the weights such that on the training set you get a good result. So if you have 1,000 or 2,000 images and you know whether there's cars or not, you can adjust the weights of this network. This is this optimization state in order to learn the computer to distinguish a car from not a car. This is also the reasons this you can do very quickly with GPUs. This is the reason why companies that are providing GPUs have gotten so big over the last few years. So in a way, this is quite interesting because what we're starting to do is we're starting to link image data and even raw data directly to a clinical outcome, just providing examples to a computer and then actually showing that we get real good performance in order to classify whether something is present in the image or whether this is a person that may possibly respond to therapy, etc. So this is a quite strong methodology, but realize that in the meantime, we're not even building a representation that that is intuitive. So that's why a lot of people are referring to these types of machine learnings a little bit as a black box, because you are building this neural network and you're optimizing so many weights, and then, what these weights really mean, you don't know. You can only just observe how the system is eventually performing. So why are we all talking about this? Now, the reason we talk about this is actually a breakthrough. I told you in the 90s, neural networks were not very popular. But in 2012, there was a breakthrough in technology. And this neural network you see, I think it's almost fair to make the statement. Maybe the transistor is even a better example, but there has been an enormous investment by academia, by industry, hundreds of billions, because of this one single neural network. This neural network was from a group from the University of Montreal, and they participated in a challenge to try to define objects in an image. And this was organized by Stanford, and you had a large database of annotated data, so you were provided with a lot of data to train on, and people were competing both with machine learning, deep learning algorithms, but also with knowledge-based algorithms. And every year you saw that the performance of algorithms improved. But in 2012, all of a sudden, this network outperformed all other methods, and it was the first time that the learning-based method outperformed knowledge-based methods. It actually did outperform the other methods by that much that people thought it may be an error in the way they did the ranking. But from this moment on, people started to really get into deep learning. In my field, medical imaging, so this is the field of computer vision. In my field, in 2013, we had the first 2 papers in a conference with 600 papers on deep learning, 2013. In 2014, we had 15. And now we only have 15 papers out of the 600 that don't use deep learning. So within 7-8 years, the whole field of medical image analysis has become a machine learning, deep learning field because of this development. Now the question is, can we do the same? Everyone saw the potential. In 2016, Geoff Hinton, he's from the group from Montreal, made a statement which made especially not clinicians in general, but the radiologists very nervous. he basically made a quote, "For me, it's clear you have to stop train radiologists because computers are demonstrably better at interpreting images than humans." And he called the radiologists the coyote beyond the cliff that have not looked down yet. And then he was asked later on, well, how long will it take for a radiologist to be replaced? He said 5 years. So we were an image analysis and deep learning group within the Department of Radiology. So they asked us a little bit what we thought. We thought it was going to take a little bit longer, and we now know, 6 years later, that it's actually quite hard to introduce AI into the clinic. And definitely data scientists are really underestimating the complexity of human thinking in medicine. What we realize now that medicine is not just a pattern recognition problem, it is also relating the patterns to models of the patient, of the anatomy, of the physiology, etc. So I think the statement now is that anything we can do in a split second, I think that will be automated. So the moment you quick recognition, etc., anything for which you don't need to reason, for which you're not using higher order thinking, if you now earn your money because of that, you have to be worried, because then at some point that will be automated. But anything which you need to reason, I think will be a long time. It will be a long time before we have autonomous AI, and I think we should much more invest in making sure human AI and human intelligence and AI work together optimally. So my question is really, to what extent can this revolution in the field of computer vision also apply to our domain? So if I look in the early years of the career when I was in the medical image analysis, what we tried to do was make the field of radiology more objective and quantitative. So we were utilizing imaging data in order to map that to models of the brain, models of the heart, such that we could extract quantitative parameters from it, such that either if you did a study, you could utilize these quantitative parameters, or if you were a radiologist, you could make a quantitative report. Now, first, the interesting statement is the field of the radiologist has not changed so much because of AI, but my domain has changed completely. So if you're, what I said, if you like model-based and knowledge-based reasoning, I really like that. That's a little bit sad now. Almost all these tasks are done better by machine learning and deep learning algorithms. So where we used to work with, within a few years, all the algorithms, 10, 15 years of many PhDs we did on quantitative image analysis, got replaced by novel algorithms that were better and faster. So the field of the medical image analysis researchers has changed dramatically, and in a way, the old-fashioned medical image analysis researcher has almost become obsolete. And there's a new, of course, there's a new type of researcher. But the interesting thing is, if you start to think about these neural nets and the power, is the fact that this started with imaging. And the reason why the AI revolution started with imaging is because they work with neural nets, and neural nets are combining information through convolution. So you actually start with a pixel, and then you start with the information around it. And images are very, it's very logical if you interpret an image to look first detailed and then in a larger region and combine the information. A lot of other information we have in medicine, take genetic information, is much more complex. It may be that things that both relate to an outcome are on the human genome very far apart. So there's a reason that AI first came to fruition in imaging. But on the other hand, the concept of building this network with a high number of degrees of freedom between input and output is in a way a little bit agnostic to what you put in, whether it's an image or clinical information or omics data or genetic data. So increasingly we see that people start, and for example, Canada is doing a lot of work in that direction, to utilize other type of data to feed into networks. And you can even think of a network that you feed in with genetic data, omics data, clinical data, medical data, and that you combine all this information in order to predict outcomes. For example, what is the risk that a patient will, the situation of the patient will deteriorate. So I think this is very exciting, is that we have now this technology to relate very high dimensional input data to even to value-based healthcare outcomes, and see to what extent the information in the data is there to solve these questions. So I really see it as a tool set. For me, AI is the big field, but the breakthrough is that we have the machinery, that if you collect your data well, that you have the machinery in order to really figure out how much information is in the data related to the outcome. Because often these relations are much more complex than what we typically do in medicine. Typically we do massively linear regressions, etc. So, and we're underusing the data. We know it's more complex, but we never had the tools to understand how to combine the different sorts of information. And now we have very powerful computational tools to let the data tell you which combination of data link to outcomes. And that is, I think, simply a machinery that is going to be useful almost in any domain. I think it's the main reason you are all here. No, it looks like, oh no. So why was this ImageNet a breakthrough? I think we have to realize that this computer vision community was an open science community avant la lettre. They had a large database, they had annotated data, they provided that freely, they had a competition, they had defined the metrics of the competition, and in this way, researchers from all of the world could compete with the same data on the same problem. I would almost say, if you have this ideal scenario, then the medical field is almost the opposite. Our data are locked, they're not available, they're in different standards, etc. People develop things, we don't know why they work, how they work. If you now go to a radiology conference, there's going to be 100 companies that all say they have great AI tools. For a clinician, it's almost impossible to know which tool works and why, etc. So it's really the field. I think the field of the medicine really has to mature a lot in order to bring this. So first we thought of replacing the radiologists in 5 years, and I now think that the field really has to mature in order to really start to make an impact. But I believe the potential is there given the power of this technology. So I think this open data resource and challenge aspect are crucial for the fact that this breakthrough came. So where could we start to apply? So if you look in Erasmus MC, if we go to the Erasmus MC situation, you realize that it's easiest to start to develop these technologies there where people have done a great job of standardizing and collecting data well and collecting data over time. So there's an important reason that my group, the initial development of machine learning and deep learning was very much linked to those studies. So we did a lot of things in the Rotterdam study, and this is exactly the type of study in which you feel, wow, such rich data sets are being collected from all the participants. We follow them up over time. So it's a very powerful to look at the technology to see to what extent information from these subjects can be linked to outcomes. And brain imaging is part of the Rotterdam study for quite some time. So here, this is already quite an old study, but I think it's really nice, and I often show it because to explain the fact that I feel that we're still underusing information in the clinic. So this is work by Marius de Groot, who looked at about 1,000 participants of the Rotterdam study, and he looked at white matter lesions, of which we know that they're linked to an increased risk of dementia and stroke. And what he did is, using image analysis techniques, put brains of people that were scanned 4 years apart on top of each other to define the white matter in 4 regions. Those regions in which the white matter looked normal, those regions which had white matter lesions at the start and at the second image, and those regions where you see new white matter lesions and where white matter lesions have grown. And those last 2 regions where the white matter lesions have grown, he specifically looked into those regions in the baseline scan to see whether the signal of MR was different. And for example, he found in the diffusion MR images, he looked at the fractional anisotropy, and that's a measure that is somehow linked to the microstructural integrity of the brain. He found that in those regions that turned out to be white matter lesions years later, already there was a statistically different signal in the MR images. And that means this, that there is information in the MR images we're not using clinically. And that is a little bit the underlying idea of trying to go to data science, etc. At this moment, if you critically reflect on clinical practice, then we're doing a number of examinations, and then with this very rich set of information, we summarize in a few quantitative numbers or even subjective measures that we provide from the diagnostic centers towards the clinicians. Whereas there's all the rich underlying data. So I think we have to challenge almost for everything we do, whether or not we can improve on our prediction if we replace the step-by-step approach with using fewer and fewer data with a data-driven approach to see whether we can better predict outcomes. So in the Rotterdam study, it means that a lot of researchers of my group, in collaboration with radiology and epidemiology, start to process this study as sort of a data science engine. We compute a lot of features, so this is the conventional machine learning, a lot of features related to the anatomy, the function, the connectivity in the brain, and we see what combination of features link to outcome. But we can do more. So that's the interesting thing of machine learning. If you, and this is work actually that a student of Kennedy did. So the previous example was that we were still computing a number of features of the brain and we were linking them to outcome. But what I said, with these neural networks, you can directly link the voxels of your image to your neural network. So what was developed here was a neural network that was trained by about 5,000 images of the Rotterdam study to try to estimate someone's age from their MR scan. If you ask a radiologist if they see a scan, at least some told me, I don't know whether, they say they can see roughly how old the person is, because depending on the number of pathologies and the rate of atrophy, they say this is a typical rate of atrophy for a 70-year-old. So if that information is in the image, you can also train an algorithm. So you can train an algorithm to compute someone's age. Now what you see is that we have a standard deviation of about 4 to 5 years. So we now have developed this very expensive method to estimate someone's age between 45 and 90, putting them in an MR scanner, run an algorithm, and then we say their age and we're 4 years off. So that's not very useful clinically. But what is interesting is that the student looked at the difference between the calendar age and the estimated age, because probably a poor lifestyle or how you feel is reflected. We know that it's reflected in many aspects in the body, so why wouldn't it be reflected in the anatomy of the brain? So building a new biomarker, which was the difference between the calendar age and the estimated age from the scanner, and following people over time, we could see that this was actually a predictor for cognitive decline and dementia, showing that you can really use the original voxels of an image in order to do this estimation. Other examples in which we've sort of turned the hospital Erasmus into a data science engine is in oncology. Martijn Starmans and other people have developed these radiomics pipelines. Basically, they try to predict all kinds of outcomes of tumors, and the way they approach is always to really rephrase what are the input data, what is the output we like to predict, collecting a large set of images, and then compute this enormous library of features and let the computer itself determine which combination of features links to the relevant clinical outcome. And one example is, for example, in low-grade glioma, there is a subset of low-grade gliomas which has a better prognosis. So in certain patients, it would be very nice if with non-invasive imaging, you would be able to identify those patients. If they're older, you may not want to go even for a biopsy because you may never go to surgery. And we see that these kind of technologies are actually, these are not perfect. The important thing is AI will simply utilize the information better than normal statistics, but if the information is not in the image, not miraculously, AI will get it out. It's still dependent on the data quality, the image data quality is still very relevant, but we have the machinery to find out for which clinical questions these data perform well, and we can estimate what is, for example, the sensitivity and specificity of such an algorithm. Now this is also work by Gennady, what I said before. We can use this for image data, but we can also use this for other types of data, genetic data, etc. We need different types of networks. Sometimes these networks can, and this is nice, I think. So first you had the model and knowledge-based approaches, then the AI came along, and now after a while we are automating everything with these deep learning methods, but we still hit the ceiling. We don't know everything. And I think that the next area we're going to actually combine knowledge-based approaches with the deep learning approaches. And one example is actually building networks that have some basis in our understanding of biology. So if you know which SNPs code for which genes are in which disease pathways, you can actually build the architecture of your network based on prior knowledge, and then utilize that network with the brute force power of deep learning in order to optimize the weights and build these networks. So what is really required for if we want to bring AI to the clinic? So first we need good data, and that means that we have to have multi-center data, and I'll say a little bit more about that later. Second, this AI is what we call still quite stupid AI, narrow AI. It's very good at linking input to output and find out what information is there. But then we really have to define input and output very carefully. And we have to know the contextual data, etc. The moment we introduce bias in the system and we would utilize that system in another situation and we train it for, strange things can happen. So we have to be very careful about that. And I think we need to validate better. At this moment, if we really want AI to have impact in the clinic, it's going to impact what we do with patients, and then we have to have a sort of the same type of rigorness in which we evaluate other types of treatments. I mean, if you're just doing AI in order to provide quantitative numbers to a biomedical research paper, okay, but if you're going to base your decision on it, then you better do some good validation. So I just want to link to a number of things that are going on and that we are actually quite involved in from our group and from Erasmus MC, because we think it's very important towards the further development of AI. So first there's HealthRI. So I think we should, within a number of years, I don't know how fast, but I think given the fact that we can learn from patients' data in order to do better prediction, we should strive for the fact that data of all patients, at least in the Netherlands, are accessible for research. I think that's a point on the horizon. We should try to achieve that. So this is the overall goal of HealthRI, HealthRI, the idea is that we would like to be able to reuse all health data in order to create better health and better healthcare and to build an integrated data structure for that. And that's of course very challenging, and at the moment there's a lot of initiatives, multi-center collaborations on certain things, but I think we need to do better. Now luckily the Dutch government, probably because we could explain the idea with COVID, I think if there was not COVID, then it would have been extremely difficult to explain politicians of the need of a data infrastructure in order to do AI research. But with COVID, everyone realizes now we need to learn from data quickly, and the government also saw that the Netherlands was not very good at doing so. So within HealthRI, we work with a lot of parties. It's a very complex project, but I think it's really a nice project. We here in Rotterdam are a node in HealthRI, and the idea is that we build a health data platform, and we do that together with the research suite. The idea is that our imaging data, our omics data, our clinical data are going to be mapped in internationally accepted standards, and they become machine approachable. Probably imaging will go first again, because imaging is easy, because the data already come out of a machine. Genetics will probably be second. Clinical information will probably be last, because it's so diverse and so heterogeneous that it's difficult to put it in common data models. But the idea is we put our data in common data models. You build a portal over different centers, So all the university medical centers are regional HealthRI nodes, and in this way you can search for data and combine data in order to develop algorithms. So this is something we built. So we collaborate here in Erasmus with the research suite. So both on the clinical data, on the imaging data and the omics data, we are defining with national and international stakeholders the standards in order to map the data to common data models. Then there's a national access portal, and we're going to support also analysis. And analysis can be done either by sending the data to a central repository or through federated learning. I think it's an interesting topic to discuss, but I think we've already done a number of projects internationally in which we build AI algorithms in which the data stay local, and you basically have a current version of a model, you dispatch the model, you optimize it, you generate a new model, and in this way you can keep the data local, but still pool them in order to build an AI algorithm. So this is sort of the vision. We should really go further. We should collect data throughout life. We should ensure that we make for all types of data international standards that we adhere to and have easy tools to map these data to these common data models. And then you can really start to do this learning at a larger scale. And I think other domains that have really opened up their data in such a way have seen tremendous progress. So it really requires a system change, but I think it's really crucial to make those steps. And I think this will really have the potential to bring a lot of AI to fruition. I think it can help us to become from being reactive and waiting for people to get ill to more proactive. I really think it can help by doing personalized risk assessment, really go towards more personalized medicine. It can empower the patients, especially if you have models and they have access to their own data, and in this way you can optimize health throughout life. Then I would like to make one final statement, and that's about validation. So I think the one thing I think the field is poorest at is really being able to tell researchers and clinicians how good their tools are. And if you go to a paper, almost every paper shows a certain performance, etc., but it's on a specific data set, and most of the times these data are not accessible or not reproducible, and then it's difficult for someone to know how well it works. Now this is an old problem. Already in 1986 in the field of image processing, someone made the claim, I just get sick of all the papers telling they do something better, but I cannot really tell because they're doing with their own metrics on their own data, etc. So I think we need to do better. Now there's a nice development, and I think what we need is challenges. Like a challenge in ImageNet, which was about labeling. I think we need many challenges in the medical field in which clinicians indicate these are applications for which AI plays a role. I have the feeling that I'm underusing the information that I have of the patient. And if you have that feeling, and if you can start to collaborate with a certain clinical or scientific community, and you start to collect your data in a more standardized fashion, and you are going to define, these are the interesting endpoints that I want to predict better, then you can build a network like the ImageNet challenge that made the revolution in deep learning. But now, if you would provide that to the community, actually people will start to work on your problem. If you open up these data sets, then people, companies, etc., will start to work on these problems and come up with state-of-the-art solutions. And in the field of medical imaging, what I really like, the American College of Radiology that we collaborate with, has defined a whole directory of use cases for AI in which they say, we want the AI to be able to perform this task. And that is, I think, the start for collecting the data set in order to collaborate with the data science community to really bring AI to clinical practice. I think I will skip, in the interest of time, the statement, but I think this is actually also a topic. It's great that we have Erasmus MC, but we should also go to convergence, because there's so many knowledge also in Delft, and there's so many people in Delft that are actually not yet really aware of what we need here in Erasmus MC, so there's an enormous opportunity there. So to conclude, I think AI is a powerful technology. It's not something mythical. It will not all of a sudden solve problems that were not solved, but at this moment is state of the art in order to get the maximum information out of your data in order to predict a certain outcome, and to really make sure that it works for you and for your application. Then we have to work on better accessibility to data and to work jointly between the clinical end users and the machine learning experts. And then once we've developed things, we really also have to think of the prospective validation and bring it into practice, because at this moment, to be honest, most approaches are still have a large potential, but few approaches really have shown real clinical value. And of course, I think as a center, as Erasmus MC, what we would like to do is ensure that this has real value in research and in clinical practice. With this, I would like to thank you, and if there's questions, I realize it's already 6 o'clock, but if there's questions, I'm happy to answer.
Thank you, Wiro, for this great talk. We still have a few minutes for questions if you like a small discussion. Feel free to ask, yeah.
Very pleasure to have a lecture today. And I have two questions. The first one is when you talked about to feed the output and input into the machine learning. The output means like the manual indication or manual measurements.
It could, in principle, be anything. Anything all information you can encode in ones and zeros. So you could have an image in and an image out. If you would like to outline, for example, the heart in a CT scan, then it could be that the input is an image and the output is also an image. But it could also be only the volume of the heart, and then the output would just be one number. So in principle, with designing your topology of your network, you're free to define all kinds of outputs. Yeah.
The second question is very specific because we are talked mostly about the deep learning based algorithm. And when we choose the words to describe this algorithm, we have a big discussion. Some authors would like to choose the automatic algorithm, some want to choose the automatic.
Automated or automatic? Okay, but I may be wrong, I'm not sure, but I would say automatic is fully automated, and automated is that there's a degree of automation. And maybe I'm wrong. That's what I think. Yeah.
Any other questions? Yeah.
I'm a doctor actually from a background, so my question is going to be a bit silly probably and basic. But say you have a camera, which is the MRI basically in the image, and you're really a fan of Canon cameras. So Canon has different setting, has a little bit different image quality than the Nikon camera, for instance. And when you make these images with your Canon, and it gets like certain pixels are always coming up with certain diseases, so you find an association.
Yeah.
But you say you need to validate with different cameras, with
Yeah.
different scanners. But maybe on the other scanner, you don't have that same association.
Yeah, no, it's a very good question actually.
Really losing information.
Yeah, so indeed, it's extremely important that you don't. It's a very good question in radiology because we have 3 main vendors in MR machines: Siemens, GE, and Philips, and radiologists will recognize the images. And so, if you train something on a Philips scanner only, it's not guaranteed it will perform the same on the Siemens or a GE scanner. I think there's 2 approaches. Either you create either you make a dedicated algorithm for every scanner. It doesn't feel correct. We start to build an algorithm which is dependent on the type of camera we use, or we input all images of all the scanners and we hope that they work. The latter is difficult, especially if you think of being a vendor. It's extremely difficult to get access to data, and you want to sell to the world. So you build something on 3 or 4 centers, and then you sell to the world, and once you've sold it, and someone doesn't like the output of the algorithm, you get a lot of complaints. So it's really an issue. There are a number of tricks in order to try to train and not focus too much on the vendor. One example is that we have certain very powerful networks. They're called generative adversarial networks. There are networks that, for example, are used to make deep fakes. If you know now that you can create a movie of someone that doesn't exist and they really look. So what you can build a neural network in order to perform a certain task, and then this neural network typically reduces the information and then expands the information. Now, at the layer where there's least information, you can use a generative adversarial network to compose the image again, and then you can build a network that you ask to predict where the scan came from. So suppose I have scans from Haarlem, Rotterdam, and Utrecht. That on the one hand, I want to perform my task. On the other hand, I want that the information that is used to perform the task is information that is not specific to any of the sites. So I let two neural networks compete with each other, and people have shown that that way of training, you actually generate algorithms that are more robust. But so there are all kinds of things to do it, but this is a typical issue. The moment you apply the algorithm in other settings than where you trained it, can be unpredictable, or is unpredictable. I think if something can be, it's
I was actually wondering, can you also use like the scanner-specific artifacts?
yeah. You could also just inform that you have the scanner, but then in case. A neural network can also know this is a Philips scanner, and then it may use it in a like you can also inform that it's a female. You can also inform the age. So there's a lot of so covariates you can put into the model at inference if you want to, and then probably the algorithm is looking at the patterns in view of these covariates. So that is something that you can do. So it's a little bit, it's interesting how it works. I've seen an overview. There's many AI tools that have been approved by the FDA, but the FDA has different classes of algorithms. And almost 90 to 95% of the algorithms are algorithms that are performing a technical task. So whereas everyone talks about the AI replacing the doctor, almost all AI tools that have been are performing a certain quantification task. This is an algorithm to quantify the size of or to detect. And the reason for it is that the moment you have an AI tool to do really clinical decision support, the FDA is asking you for much more evidence to show how it works. So there is still an enormous gap between the hype of AI and what it all can do. And if you critically reflect on all the tools that are approved by the FDA, most of them are narrow AI, and the performance, sometimes they're very powerful, but they just perform a subtask very well. And of course, this will increase, but at the moment, it is not so easy for an AI company to show clinical benefit. It's very, yes, it's costly, and the business model behind an AI algorithm is not the same business model behind a drug. So it's not so non-trivial to make the move of AI methods to really clinical decision support. And this is, so we have to think about these, how we build the evidence and how do we do prospective validation, because I think it will improve our clinical practice eventually. But we have to think of new models to do this.
So what is your most successful tool in quantitative?
So the interesting thing is that a lot of the things is that people start to organize their data and workflow better. So sometimes if I see our prostate tool, I think we have some AI in order to find the lesion, etc. But it's just that we make a recipe in which you get the data, they're organized, you get an image, etc. And you protocolize. And it's just supporting this way of working. I think a lot of people like the interface and the workflow even better, and that there's some AI underneath that is maybe not even the most important at the moment. I think we're in the beginning.
Probably one more question, and then we will try and.
Because just to also why people will have a borrow afterwards, so just can discuss also afterwards and ask questions.
Yeah.
Yeah, so we always separate supervised learning from unsupervised learning. So in case of supervised learning, you have labels, etc., and you can learn from it. In case from unsupervised learning, you can also find structure in the data, and the structure can also be used. And sometimes that leads even to new insights. So there are certain, if you collect genetic data around a certain disease, and in an unsupervised manner, you're looking at patterns, and up till now there were 4 variants known. All of a sudden you can actually see, if you cluster the data, there's actually 5 variants, that one variant there's a subvariant. So it can be even a powerful technology in order to do new knowledge discovery, to look at unsupervised. I think in the medical domain, if you look at the clinical application, I think we should just let the clinical routine provide the labels. So that is, I think, what we need to strive for, that we don't have to, because labeling is expensive, but we're spending a lot of time on collecting the data, following the patient. So ideally, you are collecting the right labels during clinical practice, and then you can use those labels and you can do supervised learning.
Okay, just to make a last comment, we can proceed with Boro. So I actually like that you showed the ImageNet network. So, but just to realize that it was based on this huge database of images, and was done in 2012. But the labeling of these images started in 2006 and was done by one person, Fei Li from US. So, and she was doing basically in the evenings, just labeling all these images like one by hand, like just to contribute to the community. That's what Wiro mentioned, like companies invested billions after that network, but actually database was built by one person doing just labeling. So that can contribute to the community a lot. So it's coming back to what we can do in the Erasmus Institute, to the challenges and standardizing. So also if you can just provide the data which can be labeled, that can improve a lot. So thank you guys.